graphs defined on groups. So if I say graphs defined on groups to you, you probably think Cayley graph. The Cayley graph is defined on the set of elements of the group. It's invariant under translation in the group. I'm going to talk about a slightly different setup where the graph is defined in terms of the group structure, and it doesn't admit translations, but it admits all the automorphisms of the group. So I'll define these graphs more formally later, but they include the generating graph, the commuting graph, and the power graph. And there are also several related graphs that can be have something to do with the study of these things. So a lot of this work is quite recent. The generating graph has become very popular recently, and I'll tell you a big result about that that just came out this year. Commuting graph goes back quite a way. Power graph began, the study of this only began this century, so these things are fairly recent. So we take a group, usually finite. Sometimes we make the further assumption that it's non-abelian and two-generated, and you'll see why I make that assumption when we come to it. Sometimes I will assume that it has trivial center, and they may look like restrictive conditions, but of course, if you're really interested in finite simple groups, then that doesn't rule anything out. All the non-abelian finite simple groups satisfy all those conditions. So here are the here will be the definitions, and also once we've defined the graph, usually the identity plays some kind of a special role. So I'll define the reduced graph in each case to be obtained simply by leaving out the identity element. There are good reasons for that, which you'll see later. So these are the rules for defining these graphs. So I give you two elements, x and y, and I have to tell you when they're joined by an edge. For the generating graph, we join them by an edge if the pair xy generates the group. For the commuting graph, we join them by an edge if they commute. That one's easy to remember. And then there's something, I'll do these in reverse of historical order. The enhanced power graph, x and y are joined if they're both powers of some element z. In other words, both x and y lie in the cyclic group generated by z. And finally, the power graph, as it was originally defined, we join them by an edge if one of them is a power of the other, but we don't say which. So you might think this should really be a directed graph, and indeed that's true, but I don't think I'll have time to discuss that much. So one of the first questions you might ask about a graph is it connected? And, apart from the generating graph, in all of these cases, you can see that the identity is joined to every element in the group. Commutes with every element in the group. The identity is a power of any element. So the question of connectedness is not interesting if the identity is in there, at least for these three. So that's the reason for leaving it out, to make the question non-trivial. Now, of course, you might be looking at a very, very large group, perhaps even the monster. You don't really want to look at the graph directly. Wouldn't it be nice if there was some simple little gadget that would answer some of your questions for you, that would be much, much smaller than the graph that you start out with? Well, for some of the questions I will ask, there is such a thing. It's the Grunberg-Kagel graph, sometimes called the prime graph of the group. So for any group G, the Grunberg-Kagel graph is defined like this. The vertex set is not the group G, it's the set of prime divisors of the order of G. So this is typically a tiny little set compared to the size of G. So in other words, it's the set of prime numbers which are orders of elements of the group. And we put an edge between the prime P and the prime Q if and only if G contains an element of order PQ. So that's the graph. And that, it turns out, encodes quite a lot of information about the kind of problems that we're going to be talking about. And it's cropped up in many other places. It's only recently that it's been realized that it has some relevance to the study of these graphs I'm talking about. But Grunberg and Kegel introduced this in the 1960s. They were studying integral representations of groups, and in particular questions like whether the augmentation ideal is decomposable and things like that. And they proved that if the prime graph is disconnected, then there are very strong restrictions on the structure of the group. But this was in an unpublished manuscript. Currently, it's become an area of very great interest. And one of the reasons that I'm glad to talk about it here is that Novosibirsk and Ekaterinburg are two of the places where there's a huge amount of work going on concerning the Grunberg-Kegel graph. And so there's that reason. There's the reason that it really is the key to some of these questions about these graphs. And the third is that Natalia and I are currently writing a paper that will explain the relevance of the Grunberg-Kegel graph to these other graphs that I'm talking about. And I'll talk about some of this work as we go through. And I'm very grateful to her for that and for the information. So here's an example. Now, I understand that this particular graph in Ekaterinburg, they call it the paw, but in Novosibirsk, it's the balalaika. It's a triangle with a pendant vertex. So there are groups that have that as their Grunberg-Kegel graph. Two of them are the alternating group A10 and the automorphism group of the Yanko group J2. For A10, you can see that there's a 7-cycle. If you take a 7-cycle, it commutes with a 3-cycle, but it doesn't commute with any element of order 2 or 5. But for all the orders 2, 3, and 5, you can find a pair of commuting elements. So the graph looks like this in the two cases. You can also see why it's called the balalaika. So these are the same graph, but you'll see that the labels 2 and 3 have swapped places. So as I said, 7 in A10, an element order 7 and an element order 3 commute, so their product has order 21, but there are no elements of order 14 or 35, so 7 is not joined to those two. So that's the Grunberg-Kegel graph. And here is a simplified version of the structure theorem that Grunberg and Kegel proved. So G is a finite group. If it has even order, I'll use pi to denote the set of primes, the connected component of the Grunberg-Kegel graph containing the prime 2. So they show that if the graph is disconnected, then G is either a Frobenius or 2 Frobenius group, or an extension of a nilpotent pi group by a simple group by a pi group. So a very restricted structure, and it's possible to use that structure theorem to do quite a lot. So, as I said, they didn't prove this, but Williams, who was a student of Grunberg, published a proof in 1981 and analyzed which simple groups have disconnected prime graph. He couldn't handle groups of Lie type and characteristic 2. Kondratyev did that in 1989, and there's another paper in 2000 which tidies it up a bit and corrects a few errors. So we have good information about groups with disconnected Grunberg-Kegel graph now. So here's the first application. You take the commuting graph. As I said, it's connected with diameter at most 2 because you can always go via the identity, or indeed via any element of the center of the group. So people who examine the connectedness of this graph typically remove the elements of the center and say, let's just look at the non-central elements and restrict the graph to those and ask whether it's connected. But I'm going to, for the other graphs, I'm simply going to remove the identity element. And so I'm particularly interested in groups whose center is trivial for this. And indeed, the theorem I'm going to state works precisely for these groups. So here's the theorem. It's very easy. A finite group with trivial center the reduced commuting graph, so the commuting graph with the identity left out, is connected if and only if the Grunberg-Kagel graph is connected. So you see we've made a big gain there. We only have to look at this tiny little graph, see if it's connected, and that will tell us whether the reduced commuting graph is connected. Okay, so I think I've got time to show you the proof of this. It's quite easy, but let me not linger over it too much. So we don't use the classification of finite simple groups. We don't even use the Grunberg-Kagel theorem. The proof is completely direct. So to prove it one way round, we suppose you've got a group whose center is trivial, and we suppose that the commuting graph is connected. We have to try and show that the Grunberg-Kagel graph is connected. So we have to take two primes P and Q and find a path between them. So we can choose elements G and H of orders P and Q, and the commuting graph is connected, so we can join them by a path in the commuting graph. And let's suppose that distance between them is D. We're going to use induction on D. If D is equal to 1, then these two elements are actually joined in the commuting graph, so they commute, so their product has order PQ, and that shows that P is joined to Q. So let's assume the result for distance is less than D, take a path from G to H, here it is, and I've written underneath the orders of the elements along the path. I'm going to start off at G, which has order P, and I'm going to go along until I first hit an element whose order is not divisible by P. That must occur because H has order Q, which is a prime different from P. So I look at the first place where that occurs. So this element has order divisible by P, this one not. So then some power of this has order P, and some power of this has order R different from P. These two commute because they're powers of commuting elements up here. So the P and R are joined in the Grunberg-Kagel graph, and R is closer to Q than P, so by induction R and Q are joined by a path, and that does it. So that's the proof one way round. The other way around, let's assume that the Grunberg-Kagel graph is connected, and we've got to go back to this huge commuting graph. So let's first observe that if you take an element which is not the identity, some power of it has prime order, so that means it commutes with it. So if I could show that all the elements of prime order lie in the same connected component of the commuting graph, I'd be done. And also, a non-trivial P group has a non-trivial center, so the non-identity elements of any CELOF subgroup lie in a single connected component. So that means if I get an element of prime order in this connected component, I get an entire CELOF subgroup. Now, the connectedness of the graph of the Grunberg-Kagel graph shows that this connected component does contain a CELOF P subgroup for every prime P, dividing the order of the group. And now, if you take an element of C and let it act by conjugation, it fixes C because it commutes with itself, it commutes with all its neighbors, and then so it fixes them, and then you work your way out. So the normalizer of this set C is G. So if C contains a CELOF subgroup, it contains every CELOF subgroup, and then it must contain all elements of prime order, and we're done. So that's very easy, but that's a typical theorem of how the Grunberg-Kagel graph contains information about the whole big graph. Okay, now I want to turn to something a little different. So we had those other graphs, the power graph, the enhanced power graph, and so on. So they each is a subgraph of the next. If you have X and Y, if one is a power of the other, then they're both powers of the same element, namely one of X or Y. So they're joined in the enhanced power graph. And therefore they commute, so they're joined in the commuting graph. So these graphs are each subgroup graphs of the next. So in particular, if you want to know whether the reduced power graph is connected, then a necessary condition is that the reduced commuting graph is connected, and you can tell that from the Grunberg-Kagel graph. What about the converse? Well, we don't know if there's an exact converse. This is all I can do at the moment. If you have a group with trivial center, and you assume that the Grunberg-Kegel graph is connected, and you also assume that there's a unique conjugacy class of subgroups of order P for every prime dividing the order of G, then it follows that the reduced power graph is connected. So it's a partial converse, but it does need this rather strong assumption here, which of course doesn't hold in many cases. So to come back to this statement that each of these graphs is contained in the next. So the power graph, as I said, is a spanning subgraph. That means it uses all the vertices and some of the edges of the enhanced power graph. That is itself a spanning subgraph of the commuting graph. And if G is non-abelian and 2 generated, then the commuting graph is a spanning subgroup of the non-generating graph, the complement of the generating graph. Because if G is non-abelian and 2 generated, then 2 elements which commute cannot generate G, and so therefore they're an edge in the non-generating graph. So this extends the hierarchy one step further. So in fact, we can look at the following graphs. We can start right at the bottom with the null graph, then the power graph, the enhanced power graph, the commuting graph, the non-generating graph, and the complete graph. And for non-abelian 2 generated groups, which as I say contain all finite simple groups, each one is contained in the next. So if you have a hierarchy like that, one thing you want to know is, when the 2 of the graphs in this hierarchy equal, when could you have one equal to the next? So I'll say a little bit about this. For which groups are 2 of these graphs equal? So if you start at the top, it's very easy. The non-generating graph is equal to the complete graph. That says that every pair fails to generate, so G is not 2 generated. Assuming that G is non-abelian, so the commuting graph is contained in the non-generating graph, they're equal if and only if G is a minimal non-abelian group. If G is non-abelian, then the commuting graph, commuting elements can't generate it. They generate a proper subgroup. That proper subgroup is abelian, but if that's equal to the non-generating graph, that says that every proper subgroup is abelian, so G is minimal non-generating. And the classification of groups with this property goes back to 1904, actually. There are 2 types, which I won't give you the details of. This is one of those things that probably was a big theorem at the time, but has been mostly forgotten now, but it exactly answers this question. Okay, so let's move one step down the hierarchy. When is the commuting graph equal to the enhanced power graph? And when is the enhanced power graph equal to the power graph? So these were studied in a paper that came out in 2017. So when is the commuting graph equal to the enhanced power graph? What does that mean? That means if 2 elements commute, then they're both powers of a single element somewhere. So that means that G can contain no subgroup isomorphic to CP cross CP for P prime. It can't contain the direct product of 2 groups of prime order because generators of those 2 groups commute, but there's no element of which they're both powers. And so that says that the Silov subgroups of G are cyclic or generalized quaternion. And we can say a lot about these groups. In fact, we can pretty much completely say what they are. So there are structure theorems that tell us what the group looks like for this equality. I won't go through all the details, but if the Silov subgroups, or if all the Silov subgroups are cyclic, the group is metacyclic, cyclic by cyclic. If the Silov 2 subgroup is generalized quaternion, then there's a central involution modulo the odd order subgroup. Factor that out and you get a group with dihedral Silov 2 subgroups. And that classification goes back to Gorenstein and Walter in the 1960s or 70s. Right, so now what about enhanced power graph equal to the power graph? That says if 2 elements are both powers of the same element, then one is a power of the other. And that's equivalent to saying that there cannot be a cyclic subgroup of order PQ. In other words, there cannot be CP cross CQ, where P and Q are distinct primes. So what does that say? There are no subgroups of order PQ, no elements of order PQ. So the Grunberg-Kagel graph of G is the null graph. It has no edges at all. So this is exact criterion for these two graphs to be equal is that the Grunberg-Kagel graph is the null graph. And so this is one of the things that Natalia and I are working out. So we hope to publish a complete classification of all these groups soon. There are various simple groups that occur, a relatively small number, but there are at least enough to make the question interesting, I think. So that's the enhanced power graph equal to the power graph. The final case would be, when is the power graph equal to the null graph? Well, it can't be if G is not the trivial group, because the identity is always the power of any non-identity element. So that tells us when two of these graphs are equal. Right, having decided that, you might want to go on and say, what about the differences between these graphs? So take two successive graphs in the hierarchy and look at the difference between the edge sets. So the pairs that are edges in the larger graph, but not in the smaller graph. So let's start at the top again. The difference between the complete graph and the non-generating graph is just the generating graph. So two elements joined if they generate the group. And there's a remarkable recent result on this by Bernes, Guralnik, and Harper. They've proved a fairly long-standing conjecture. So this is what the theorem says. If you have a finite group G, the following three conditions are equivalent. First one says the reduced generating graph has no isolated vertices. That means, apart from the identity, if I pick any element X, I can find some element Y such that X and Y generate the group. So any element, you can find one to pair with it to generate the group. The second statement is any two vertices of the reduced generating graph have a common neighbor. Now you see that is apparently much, much stronger, because it says if you take any two vertices, X and Y, you can find Z such that X and Z generate and Y and Z generate. So it's really a considerably stronger condition on the face of it, but it's actually equivalent. And the group theoretic equivalent is that every proper quotient of G is cyclic. So in particular, these equivalent conditions hold for every non-abelian simple group. And it was observed that, well, it was proved that this held in every simple group. It was observed that this appeared to hold, and now we have a proof of this. So that's a big result about the generating graph. So the difference between the non-generating graph and the commuting graph, this is the next difference. So the graph whose two vertices are joined by an edge, if they don't commute, but they don't generate the group. And as I said, as long as G is not a minimal non-abelian group, this graph has some edges. And Saul Friedman, a PhD student in St. Andrews, has studied this and has got some detailed results, which I'm not going to explain here. But in particular, for nilpotent groups, there's a complete determination of when this graph is connected. So the next one is the difference between the commuting graph and the enhanced power graph, and the difference between the enhanced power graph and the power graph. To my knowledge, nobody has looked at any of those yet. If you want to try your hand at it, the field is completely open, I think, so go ahead. The final one is the difference between the power graph and the null graph, which is just the power graph. As I say, this was less than 20 years ago that the power graph first appeared in the literature, and already there are quite a large number of papers. And most of what I will say for the rest of the talk will concern the power graph. And I want to deal with two main areas: forbidden subgraphs and automorphism groups. Right, so this might be a good point to stop and say, does anyone have any questions at this point? No, apparently not. Okay, let's press on. So I will be talking about certain important classes of graphs. In all cases, these graphs will have two definitions, one a structural definition and one in terms of forbidden induced subgraphs. And possibly the most famous of these, which go back to Claude Berge, is the class of perfect graphs. So a graph is perfect if every induced subgraph has clique number equal to the chromatic number. In other words, the size of the largest complete subgraph is equal to the smallest number of colors that you need to color the graph properly, so that no two adjacent vertices get the same color. So obviously the chromatic number is at least the clique number for any graph. If they're equal for every induced subgraph, we call the graph perfect. So this was defined by Claude Berge, and he conjectured a forbidden subgraph characterization, which was proved much later by Chudnovsky, Robertson, Seymour, and Thomas. A graph is perfect if and only if it has no induced subgraph, which is either a cycle of odd length greater than 3 or the complement of such a thing. And you can see this one way around very easily. If you take, for example, a 5 cycle, if the graph had an induced 5 cycle, the largest complete subgraph of a 5 cycle is 2, but you cannot properly color it with 2 colors. You need 3, because if you go red, blue, you'll need a third color for the last vertex. So a graph that contains an induced 5 cycle is not perfect. And if you rule out all induced cycles of odd size and their complements, you get a characterization of perfect graphs. So when is the power graph perfect? And you could ask the same question for the other graphs, but I'll concentrate on the power graph. Well, the power graph of any finite group is perfect. This is quite elementary, and I won't show you a proof. But when I defined the power graph, I mentioned that you might think it should be a directed graph. We join x and y if one of them is a power of the other. But you might say we should put a directed arc from x to y if y is a power of x. So if you think about that directed graph, you will see that it is a partial preorder. That is, it's a reflexive and transitive relation. And the power graph is the comparability graph of that partial preorder. And it's not too hard to show that the comparability graph of any partial preorder is perfect. And therefore the power graph of any finite group is perfect. So they're all perfect. So we're within this class of perfect graphs when we look at the power graphs. I want to talk about some results that I proved with Pallavi Manna and Ranjit Mehetari. Quite recently, they're on the archive now. I'll give you the references at the end. But I need to introduce two subclasses of the perfect graphs, the threshold graphs and the split graphs. A threshold graph is a graph that you can build from the trivial graph by two operations. You're allowed to add an isolated vertex, or you're allowed to add a vertex joined to every other vertex. So these are graphs with a particularly simple structure. And in fact, you can show that a graph is a threshold graph if and only if it does not contain a cycle of length 4 or a path of length 4 or two disjoint edges as induced subgraph. So that's the induced subgraph characterization. So they're particularly simple. So they have very good algorithmic properties. If you want to find out anything about a graph, if it happens to be a threshold graph, there's a very efficient algorithm probably. And a split graph is a graph whose vertices can be divided into two subsets, one inducing a complete graph, the other a null graph. So you have a complete graph, and a null graph, and some edges between them, arbitrary edges between them, but every vertex lies either in the complete or in the null graph. And the characterization here is that a graph is a split graph if it doesn't contain a cycle of length 4 or 5 or 2 disjoint edges. Now, 2 disjoint edges turns out to be the key property. Forbidding 2 disjoint edges is part of both of these. And so this is what our theorem says. If you want the power graph to be a threshold graph or a split graph, those are equivalent. So the power graph is a threshold graph if and only if the power graph is a split graph. And which are the groups? Well, there aren't that many of them. Cyclic of prime power order, elementary abelian or dihedral 2 group, cyclic of order twice an odd prime, dihedral of order twice a power of an odd prime, or dihedral of order 4 times an odd prime. So that's the complete list of groups where the power graph satisfies one or other of these conditions. And indeed, the real condition that you use is this forbidding 2 disjoint edges. If you have a group whose power graph doesn't have 2 disjoint edges in it, then it must be one of this short list of graphs. So those are all the groups whose power graph is threshold or split. So for the next 2 classes, we've only been able to deal completely with nilpotent groups. And in the second case, I have some ideas about going beyond, but we don't have definitive results yet. So a graph is chordal if every circuit of length greater than 3 has a chord. So if you find any circuit in the graph, if its length is greater than 3, then there will be a chord dividing it into 2 shorter circuits. So all the minimal circuits have length 3. So that's a chordal graph. And again, chordal graphs are an important class with good algorithmic properties. And here's the theorem for nilpotent groups. It should say the finite nilpotent group there. I'm sorry. The finite nilpotent group, G, has the property that the power graph is chordal if and only if it's either a P group for some prime P, or the direct product of a cyclic group of prime power order and a group of exponent Q, where Q is a prime different from P. So that tells you about the nilpotent groups whose power graphs are chordal. And the final class, this is a class that, this is one of my favorite graph classes, cographs they're usually called now. I tend to call them n-free graphs. They're graphs that can be built from the one vertex graph by the operations of disjoint union and complement. So you're allowed to take graphs that you've built so far, take their disjoint union, or take the complement of that. They are precisely the comparability graphs of partial orders that can be built by Nessing and crossing. So this roughly means disjoint union or ordinal sum of partial orders. A graph is a cograph if and only if it doesn't contain the path on 4 vertices as an induced subgraph. And the final characterization that I don't think I wrote down is cographs have the, if you're a cograph, either you're disconnected or your complement is disconnected. So there's a kind of tree-like structure for these things. If the graph is disconnected, it's built out of smaller cographs. If its complement is disconnected, then the components of the complement are smaller cographs. So a nilpotent group has the property that its power graph is a cograph if and only if either it is a group of prime power order or it's cyclic with order just the product of 2 prime numbers. So we seem to be getting back to the Grunberg-Kagel graph here, and indeed we are, and that will come into any final classification of these groups, though we don't have that yet, because this tells you about the nilpotent subgroups. So we have a necessary condition and a sufficient condition in terms of the Grunberg-Kagel graph. If the Grunberg-Kagel graph is null, so if there are no edges in the Grunberg-Kagel graph, then the power graph is a cograph. And if G is non-solvable and the power graph is a cograph, then all components of the Grunberg-Kegel graph, except possibly the component containing prime 2, are isolated vertices or edges, so contain either 1 or 2 vertices. So these conditions aren't the same, but having power graph or code graph is sandwiched somewhere between them. But there cannot be a necessary and sufficient condition purely in terms of the Grunberg-Kegel graph for the power graph to be a code graph. If you look at the groups PSL211 and M11, so this one has order 660, this one has order 7,920. These are not too big. You can actually do the computations very quickly. They have the same Grunberg-Kegel graph, so they have an edge from 2 to 3, an isolated vertex 5, and an isolated vertex 11. But the power graph of the first is a code graph, and the power graph of the second is not. So this shows you that they both fit between these two. The GK graph isn't null, it contains one edge, but every component without exception is either an isolated vertex or an edge. And yet one has a power graph, a code graph, the other not. So that's where we are with that at the moment. But just let me say one more thing. This is, if you like, a challenge to the number theorists. For giving a complete classification of groups whose power graph is a code graph is not likely to happen anytime soon, because you run into some hard number theory problems. So for example, let's just look at the case PSL2, 2 to the m. If you look at the Grunberg-Kegel graph of this group, you find that there's one component containing the prime 2. There's one component that has all the prime divisors of 2 to the m plus 1, and there's one component that has all the prime divisors of 2 to the m minus 1. And you can show that the power graph is a code graph. Now, remember that thing about the nilpotent groups. There's a cyclic group of that order, and there's a cyclic group of that order. So if the power graph is going to be a code graph, each of these numbers had better be either a prime power or the product of two distinct primes. And which powers of 2 have that property? Well, it's in the sort of the same spirit as the existence of Fermat and Mersenne primes. They're not equivalent. If you have, let's say, a Mersenne prime, so that you know that 2 to the m minus 1 is prime, perhaps 2 to the m plus 1 is a product of just 2 primes. Well, you can easily see that one of those primes has to be 3, but, I didn't mention, if you work out m equals 11, you find that 2 to the 11 minus 1 is equal to 23 times 89, and 2 to the 11 plus 1 is 3 times 683. So PSL2, 2 to the 11, the power graph is a code graph. So for graphs with trivial center, connectedness of the Grunberg-Kegel graph is equivalent to connectedness of the commuting graph. Are there other relations between a relation between other properties of the Grunberg-Kegel graph and the other graphs we've been considering? So we've seen that this graph has relevance to the power graph and to the enhanced power graph. So there are definitely connections there. But does it go back the other way? There's a paper that Natalia pointed me to showing that it often happens that the Grunberg-Kegel graph is a split graph. That is, the vertices are the disjoint union of a complete graph and a null graph. Does that have implications for either the commuting graph or the power graph? I don't know. And other questions, when are other graphs that we have considered perfect graphs? So like the enhanced power graph or the commuting graph. And John Britnell and Nick Gill have some partial results for the commuting graph, but this question is only partly solved for the commuting graph and not at all for the enhanced power graph. There again, I have some ideas about how that might go. Right, now I want to say a little bit about automorphism groups. anyone who's tried to look at the automorphism groups of these types of graphs have run up against a problem. There are sets of vertices that have the same neighborhood, and so they can be permuted arbitrarily. And these graph automorphisms have no connection with the structure of the group. So let me just give you a very simple example. Let's consider the generating graph of the alternating group A5. So the vertices are the elements of A5. We join two of them if they generate the group. So if we take two elements that generate the same cyclic subgroup, so let's say A, we take an element A of order 5, and then we take also A squared. Well, if A and B generate the group, so do A squared and B. So A and A squared have the same neighbors. And that means that the four powers of A can be permuted arbitrarily by graph automorphisms. And you get 6 disjoint sets of 4 vertices like that, and 10 disjoint pairs of vertices from the elements of order 3, and they're completely indistinguishable in the graph. So we've got this normal subgroup S4 to the 6th times S2 to the 10th, rather large, of absolutely no interest whatever, but it slows down the computation. So you need to be able to get rid of those things. And it may make sense to factor out things like that, but the trouble is that sometimes you factor out too much and you change the automorphism group you're looking at. We have examples where that happens. But I'll just give you one fact here. So there's a paper by Ashrafi, Khalami, and Maranian in 2017 about automorphism groups of power graphs. And they made a conjecture which caught my eye. So you let F be the class of groups obtained from the trivial group by the operations of direct product and wreath product with a symmetric group. So you're allowed to take the direct product of groups that you've already built, or you can take a group, take the direct product of m copies of it, and then permute them arbitrarily by elements of the symmetric group. And their conjecture was that the automorphism group of the power graph of any finite group belongs to the class F. Well, that's not actually true. M11 is a counterexample. And I'll just say a little bit about M11 here. If we take the reduced power graph of M11, then it has a lot of uninteresting bits. There are 144 complete graphs of size 10 corresponding to the elements of order 11. You see, in a subgroup of order 11, any two non-identity elements are powers of each other. And these are not joined to anything else, so they're isostack components. Then similarly, the elements of order 5 give you 396 complete graphs of size 4. Obviously, this part is of no interest. What's left is a single connected component on the remaining 4,895 vertices. It has a huge automorphism group with thousands of digits, but most of this is rubbish. So if you take this graph, you first of all look at the relation between vertices of having the same closed neighborhood. So vertices that have the same neighbors, including themselves. Factor that relation out, and then the graph that you've got left, factor out the relation of having the same open neighborhood. You've got rid of all the rubbish at that point. And if you check along the way, you will find that you haven't actually lost anything. You get this huge normal subgroup, but the quotient group is precisely the automorphism group of the graph on 1,210 vertices that you have left, and that's M11. So M11 is a quotient of the automorphism group of its power graph, and therefore that is a counterexample to that conjecture. But on the other hand, if the automorphism group of any cograph belongs to F, this is an elementary fact to prove. You can prove it as an exercise. It's not a characteristic property of cographs because automorphism groups of trees all belong to F. Any tree has either a center or a bicenter, that is, there's a vertex or an edge fixed by the automorphisms, and then you just build out from that. And the automorphism groups of almost all random graphs belong to F. Well, Gareth told us about finite random graphs yesterday. Edish and Rainey showed that they almost all have the trivial automorphism group. So this is a rather stupid reason for belonging to F, but they do at least belong to F. So as a corollary of this, if G is a finite group whose pal graph is a cograph, then the conjecture of Ashrafi et al. Is true for G. The automorphism group pal graph belongs to F. Right, I will just end up by switching to a different topic. I think I can do this in 5 minutes. The intersection graph, because this is not a graph defined on the elements of the group, but the techniques used for studying it are rather simple. So the intersection graph of a finite group is defined like this. The vertices are the non-trivial proper subgroups of the group, right? The subgroups that are not the whole group and not the identity. And two vertices are adjacent if their intersection is non-trivial. So that's the intersection graph of the group. And it's related to the generating graph because two elements are adjacent in the non-generating graph if and only if they're contained in a proper subgroup. So here are 3 quick remarks about these things. The intersection graph has at least one vertex. That means there's at least one subgroup, which is not the whole group or the identity, if and only if G is not cyclic of prime order. So that's okay. Every proper subgroup is contained in a maximal subgroup. So if you're trying to decide whether the intersection graph is connected, it's enough to look at maximal subgroups. If you can find a path of length D between any two maximal subgroups, then there's a path of length at most D plus 2 between any two subgroups. And the final thing is that if G is not a dihedral group, then any two subgroups of even order lie at distance at most 2, because each contains an involution. The involutions generate a dihedral group, and that means you can get from one subgroup to the other in 2 steps. So there are some elementary observations. So this definition goes back to 1969, and Ciccani and Pollack showed that if the group is not simple, well, they determined when the intersection graph is connected and showed that if it is connected, its diameter is at most 4. What about simple groups? Well, nothing happened for a long time. I don't know why. Shen proved in 2010 that the graph is connected, but he didn't give an upper bound for its diameter. Herzog, Longobardi, and May showed that the diameter is at most 64. Ma reduced this to 28 in 2016. This year, Saul Friedman showed the correct bound is 5, which is definitely better than 64. So the bound 5 is attained by the baby monster. And any other group attaining the bound must be a unitary group of prime dimension. So what about unitary groups? It's known that the diameter can be 3, 4, or 5. There are unitary groups where the diameter is 3, or 4, or 5. But there is not yet a determination of which unitary groups realize which possible value. So, but anyway, a group with the maximum diameter is either the baby monster or one of some of the unitary groups of prime dimension. So that concludes my talk. I have some references here, which will be in the slides, which I'll send to Elena shortly, but I will stop there. So thank you for your attention.
Thank you very much, Peter, for your nice talk. Are there questions to Peter?
I have a question for Peter.
Yeah, sure, please.
Yes.
Has anyone ever looked at the generating graph for a permutation group, where the vertices are the group elements, and there is an edge between two vertices if they generate not the whole group, but a transitive subgroup? So for example,
yes.
the generating graph would be for the regular representation,
Yes.
It would allow any faithful representation.
That's an interesting idea. I don't know anything about that. Certainly it is true that you can build a whole slew of graphs by saying, we'll take two elements X and Y and we'll join them if the group that they generate has some product, some property.
Yeah.
No, I didn't say when I was going through, but for the enhanced power graph, you join X and Y if the group they generate is cyclic. For the commuting graph, you join them if the group they generate is abelian.
Yeah.
This question has been looked at when the group is nilpotent. And as you say, the generating graph, the condition is the group they generate is the whole group. But you could certainly ask about proper subgroups with some property, and being a transitive subgroup looks like a very nice property to do. I don't know anything about that, but it looks like a very nice question.
Okay, thanks.
Okay, thank you. Are there any other questions?
I'm sorry, Andrei Vasiliev. Can
Sure.
I do some
Yeah.
comment? Peter, you mentioned the paper by Mark Lewis and all, and I'm
Yes.
one of the authors of this paper. So I would like just to say what it is really proved there.
Yeah.
Actually, it is easy to see that if you take finite simple group, then its prime graph of Greenberg-Kegel graph is not necessarily split. But if you factor out this graph by the relation to have same close neighborhood,
Yes.
yes, then
Yes.
it will be true. This is the main result of this.
Okay. Yes.
So if you take a prime graph, factor on this relation, then you will always get split graph. That's
Okay, thank you very much. Yes, I only learned about this result this week, so I haven't had time to look it up yet, but thank you for that information. A lot of this, these slides that I've shown you are very different from the ones that I had prepared at the beginning of the week, because so much has happened in the meantime. But anyway, so thank you for that.
Yeah. Okay, are there any other questions? Comments? Remarks? Well, okay, Peter, thank you very much for this nice talk and for showing us some open fields on graphs defined on group. Thank you very much.
Okay, thank you.